You are in the operations room of a huge radar system that is hastening man's entrance into the space age. This is an Air Research and Development Command facility for tracking missiles and space vehicles. Vital data is being gathered on radar refraction in the ionosphere, the interference effects of sunspots and solar and galactic noise in space communications. The equipment is the U.S. Air Force's giant FPS-44 on Trinidad Island in the West Indies. It is typical of a number of super powerful radars that have been designed, produced, installed, and are operated by General Electric's Heavy Military Electronics Department. The skills and technical talents required to successfully accomplish modern electronics projects such as this are a far cry from the relatively simple needs of the small black boxes of a few short years ago. This project, for instance, called for the removal of a mountaintop. Thousands of yards of concrete were poured to form the footings for the antenna. Steelworking skills were brought into play to erect the giant reflector. A 109-ton organ pipe scanner directs the energy from radar transmitters that are among the most powerful in the world. Engineering data from the experiments performed here are processed and analyzed in our digital and analog computer facility in Syracuse. Solving the problems encountered in the incredibly complex job of national defense in this missile age takes the ability to do jobs like this, or this, from this to this, from the simple to the complex, from components so small that hundreds can be held in the hand, to radar systems with antennas larger than football fields. This is our business. Here at General Electric's Heavy Military Electronics Department, we are organized specifically to develop, design, manufacture, and provide customer service on large advanced military electronic equipment and systems. We work with nearly all the things that make up a military electronic product. The skills and knowledge growing out of the development of components, for example, is reflected in the most complex of our products. We've turned out a number of advanced development components, all of which have made material contributions to our system's work. Here is an encapsulated memory plane for defense computer systems, the first able to withstand severe environmental conditions. We make electrically variable delay lines, wire sonic delay lines, custom designed shift registers, ceramics such as lead metaniobate and barium titanate, and microwave ferrites. This new solid-state parametric amplifier made possible the reception of Pioneer 4 signals through more than 407,000 miles of space. This was 4 days after launching, with the satellite transmitting a signal of less than 0.2 of a watt. Because the easily tuned amplifier cut receiver noise to a mere whisper, our tracking station used a standard dish antenna, only 18 feet in diameter. Continual progress in component development has contributed greatly to our record of success in solving the larger problems of defense electronics. Successes like this, for instance. How do you guide an ICBM to a target on the Earth or into an orbit in outer space? Little or no previous work had been done in this field when our people accepted the project in late 1954. New areas of information had to be uncovered, basic theories established. The resulting radio command system proved its extreme accuracy by guiding the Atlas into orbit in Project SCORE. Even as this dramatic success was realized, we were turning to the problems of refining the system. A more recent version of the ground guidance equipment has been significantly reduced in size through transistorization. Its modular design permits ready access to all sub-assemblies. A single diagnostic center provides all indicators for maintenance and operation of the equipment. If a fault should occur in any part of the system, its location is immediately indicated by module number. In a matter of seconds, it can be replaced with another unit. Each improved technique revealed by continuing study is utilized to increase reliability of the system. Here is the answer to another space-age problem, a system that will give early warning of enemy ballistic missile attacks. These powerful radars installed at sites in the far north will serve as the first-line eyes of the ballistic missile early warning system. RCA is the Air Force's prime contractor on this program. GE is responsible for the design, manufacture, installation, and checkout of the surveillance radar portion. Much of the development work on the more than 2,000-mile range radars was performed in our high-power test laboratory at Syracuse. The demands of the space age cannot be ignored. But here is another challenge. Manned aircraft are still a threat and will be in the foreseeable future. And radar eyes are needed to spot them, too. The problems of detecting both jets at 70,000 feet and prop-driven planes flying right on the deck in a realistic battle environment were solved with a number of high-power, versatile radar equipments. One example is the long-range FPS-7, which determines height as well as range and azimuth on every look at the target. Part of its success is the result of this very high-power L-band klystron tube developed by General Electric engineers in Syracuse, Palo Alto, and Schenectady. Another development, the FSA-12 uses the information from the stacked beam radars to automatically detect and track hundreds of aircraft simultaneously. Its automatic function makes it the first of its kind. In all radar systems, there is a universal problem. What do we do about enemy jamming? This man is the anti-jam operator. He works at the anti-jam console of our recently delivered FPS-24 frequency diversity high-power search radar. This system enables him to pre-select the type of jam protection needed for various areas surveyed by the radar. For reliability and maximum effectiveness against electronic countermeasures, all electronic equipment in the system is in duplicate. Reduction of effective enemy jamming and increased range are also features of this high-power acquisition radar used with the Nike Hercules improved system. Built for Bell Telephone Laboratories and Western Electric, it incorporates the new General Electric IF moving target indicator. This enables it to detect small air-to-surface missiles at great range and altitude, as well as advanced design strategic bombers, despite severe electronic countermeasures. With the advent of supersonic aircraft, resolution of data from high-powered long-range radar could no longer be computed manually at the plot board. In answer to this problem, HMED produced the ANGPA-37, the first mass-produced equipment to introduce semi-automatic tracking and automatic computation of the intercept problem. Since 1955, this radar computer tracking group has been capable of automatically computing and disseminating data on many separate interceptions at one time. The data link GKA1 portion of this integrated group was also developed and produced by HMED. The continuously computed data on each of the targets is sent only to the particular interceptor assigned to that target. Here's another problem: how to integrate all the electronic devices required for the nation's extra-continental defense, either of a single site or of a continent. The Heavy Military Electronics Department has accepted the complete technical and management responsibility for the 412L Air Weapons Control System, which will solve this problem electronically. Combining mobile and fixed stations, the highly sophisticated electronic system will provide the Air Force with defense capabilities for areas outside the United States. So far, we have been considering missile and air defense systems. But there's still another problem: defense against attack from the depths of the sea. Sonar is a major part of the answer. In our sonar laboratory, refinements have been made in this field which make small targets easier to detect and classify. Some of our special high-resolution sonar gear was used by the nuclear-powered Nautilus and Skate on their voyages beneath the North Pole ice cap. A troublesome barrier to effective sonar application has been the difficulty of extracting the useful signal from interference. Using a new concept of delay line time compression, or deltic, this latest GE signal processor separates the critical transmitted and received signals from ambient noise and reverberation. HMED has recently tackled another problem for the U.S. Navy: the difficulty of communicating a firing command to submerged Polaris-equipped submarines. General Electric has been selected to study and supply equipment to evaluate the many methods that could be used for the Polaris Command Communications Network. And on the land battlefields, another problem: to provide our ground forces with electronic field equipment to meet modern limited warfare requirements. The T7 chronograph quickly and accurately measures muzzle velocity in the field. This enables battalion commanders to group together guns of like characteristics, as well as check variances in ammunition lots and barrel wear. The result: more accurate shooting. The TPQ-10 was developed for automatic direction of close support aircraft. It's a frontline system that can be transported by 2 helicopters, and on the ground is easily handled by a small crew. This MPQ-4 pinpoints location of enemy mortars by using information supplied by an enemy shell passing through its 2 narrow radio frequency beams. Operational within 15 minutes of its arrival on the battlefield, this mortar locator utilizes a computer to quickly process target data from anywhere in its 6-mile range for fast counter-battery fire. Innovations in manufacturing and checkout techniques were made in production of this equipment. In developing, designing, and manufacturing antenna systems, often involving new theories and techniques, another important problem appears: accurately measuring their performance. Antenna Park is an ideal facility for our testing. The long, deep valley close to our Syracuse headquarters is a near-perfect location for pattern testing. The operational reliability of each equipment is predictable after it has been subjected to the various environmental tests: extremes of heat, cold, and rough treatment. Further test facilities are provided by the General Electric Flight Test Center at Schenectady. Here is an airborne laboratory for testing electronic systems in actual flight. The Flight Test Center also supplies modern aircraft to act as realistic targets and prove the performance of the radars and electronic ground environments developed by HMED. Delivery of the equipment doesn't bring an end to our contributions. Military personnel must be trained to operate and maintain the highly complex gear. At Syracuse, we have established a school which offers specialized courses to familiarize both operational and maintenance personnel with aspects of defense electronic equipment. Our training people also go into the field to set up classes at military sites for on-the-spot instruction. Another post-delivery service: installation, on-site and depot level maintenance, and modernization of equipment. Heavy Military Electronics Department product service people go all over the world to back up the military and their prime contractors. They analyze equipment failures so that design and production engineers can make improvements, and they take full system responsibility for high-priority projects for the customer. Problems? We thrive on them. Today, in our research laboratory, scientists and engineers are prying into the future seeking new information and new ways to solve the problems of tomorrow, to better utilize man's resources. In our electronics laboratory, the new knowledge is being applied to develop innovations in techniques, materials, components, and devices. This is the bridge from basic research to better products in radar, sonar, communications, data handling, and information display equipment. For instance, work with solid-state materials is improving the efficiency of capacitors and sonar transducers. Ferrites are being developed for use in phase shifters for applications in new electronic scanning devices. Another example is the use of thermoplastic recording in the development of a new technique for large screen information displays. Radar data will be both recorded and projected in less than 1 second while maintaining an extremely high degree of resolution. All along the line, from research and development to field service. From components to complete systems, equally important advancements are being created by specialists in each phase of the process. These are the talents and skills that have been developed and proved in solving defense problems of the past. This is the demonstrated competence that is ready to help you solve the next defense problem.